In this video, I am going to explain about the substituents and effect of substituent on reactivity, orientation on monosubstituted benzene ring. In this topic, we will study about the monosubstituted benzene ring and the other substituent, how they react on benzene ring. So this reaction is also called as electrophilic substitution reaction on monosubstituted benzene ring. First, we should know about what is electrophile and what is electrophilic substitution reaction. If you want to know about electrophile, then I already made a video on electrophile and I will share the link in description box. Just I am explaining a brief introduction about electrophiles. Electrophiles are the positive charge species which are electron deficient. Now let's see what is monosubstituted benzene ring. As we all know the structure of benzene, it has 6 carbon and 6 hydrogen. So this is the structure of benzene where carbon they are present here at the terminal and they are bonded with one hydrogen. So in case of electrophilic substitution reaction, this hydrogen is substituted with one functional group. So we can substitute any of the hydrogen with one functional group. As benzene has 6 carbon and 6 hydrogen, we can replace one of the hydrogen by functional group and benzene will become monosubstituted. Means one substituted functional group is present on benzene ring. Let's see if we will replace this hydrogen with G. G can be any functional group. So this structure will become monosubstituted benzene ring. So in this topic, we are going to study about this effect of monosubstituted ring on the substitution or at other position in benzene ring. Means if one of the hydrogen is replaced by the functional group, how it will affect the substitution on other position. So that is called the effect of monosubstituted benzene ring or monosubstituted aromatic ring, that when one of the hydrogen is replaced by the functional group, then how it will affect substitution of other functional group at different position. So here we know that benzene has 3 position, para, and this is ortho position and this is meta position. So if one of the functional group will present here, this is the monosubstituted benzene ring. If one of the hydrogen is substituted with a functional group, so the remaining positions where no functional group is there is ortho, meta, para, meta and ortho. Means this is first position, second position, third position, fourth and fifth. If at first position one group is already present, here a group is there, it can be any group. So the remaining position which are unoccupied is 2, 3, 4, 5 and 6. These are the positions second, third, fourth and fifth where substitution can take place because presence of hydrogen is there, so that hydrogen can be substituted with some other functional group. So first position is already occupied by one functional group. The remaining second, third, fourth, fifth and sixth position is available for the substitution reaction. Effect of substituents on reactivity indicate if this A group is present on the benzene ring, how it will affect the reactivity on this position. Means if any other functional group like B wants to react or wants to substitute with this benzene ring, the A will decide where the B functional group will substitute in these given position. I am repeating again. If A is the functional group present on the benzene ring and B is the second functional group which we want to substitute on benzene ring, then the presence of A will decide at which position this B group will be substituted. That is called the effect of monosubstituted benzene. So means if the benzene is already substituted with one group, that functional group will decide the substitution on benzene ring. Let's take an example. This is our monosubstituted benzene ring. It is substituted with S group. Right now I am not writing any particular functional group, just writing a common example so that you can easily understand. So this is our monosubstituted benzene ring. It reacts with electrophile, let's see A, another group. So there are three possibilities. As you can see, already one functional group is there on benzene ring. When it will react with other functional group, then there are three possibilities of formation of three types of products. Okay, so first is your ortho type. In this case you can see the A group is substituted at ortho position, so that is called ortho product. This is the first possibility, first case. Second possibility is that this A second group will substitute at the para position, so that is the para product, means the substitution will take place at para position. Third possibility is the substitution at meta position. So these are the three possibility of formation of product. Whether the ortho, para or meta product will form, it depends on this group, S group, which is already present on the benzene ring. So that is why it is called as effect of substituent, which is already present on the benzene ring. Because S already present on this ring, it will direct A to attach at either ortho or at para or at meta position. So here we can simply understand that if one functional group is present on benzene ring, then the other functional group will attach at either ortho, para or meta position, but that attachment will be directed by this group, S group, which is already present. So that is why this S or the group which is already present on the benzene ring is very important for orientation, because this S will only decide where this A will get substituted, at which position this will be substituted. Let's take another example. So here you can see benzene with OH group, that is phenol, and this is benzene with carboxylic group, means benzoic acid. And if nitration reaction will occur, it react with nitric acid in the presence of H2SO4. Just H2SO4 will act as a catalyst. Let's see what are the products formed in this reaction. Here you can see the phenol and benzoic acid is there. When they react with nitric acid in the presence of H2SO4, there are possibility of three different types of products. So in first case, this is the ortho product where nitro group is substituted at ortho position. Second product can be nitro product where the NO2 group is substituted at nitro position, and here the NO2 group is substituted at meta position. The same thing in case of benzoic acid. In first case ortho product, in second case para product, para nitro product, in third case this is the meta product. So these are the possibilities of formation of product. So in first case you can see when phenol is there, 58% ortho product will form, 41% para product will form, and only 1% meta product is formed. So we can say that if hydroxy group is present, then we will get ortho and para product. So if hydroxy group is present, it is giving maximum ortho and para product, 58% ortho product and 41% para product. So this OH group direct NO2 group which is obtained from nitric acid. So this OH group will direct nitric acid to go at ortho and para position. So here you can see 58% and 41% this ortho and para product is formed. Meta product is just 1%. Let's see the next case in which benzoic acid is there. So here you can see if COOH group is there, 85% meta product is obtained, meta nitro. So it means that COOH group will direct NO2 group to go to meta position. position. Remaining para product just 0.4% and ortho product is 14.6%. So we can say that the carboxylic group is meta-directing group. Why meta-directing group? Because it will direct the other functional group to go at meta position, just like NO2. So now we know that if one functional group is already present on the benzene ring, it will direct the other functional group to react at the remaining position. Means the first substituent will direct the second substituent in the benzene ring. So that is why the effect of monosubstituent ring is more. If one group is there, it will direct the other group to react or to substitute at other position. So basically this presence of functional group will decide or direct the substitution of second functional group at various positions. Now let's see the examples which are ortho-para-directing group and which are meta-directing group. So here I am writing the examples of ortho-para-directing group and meta-directing group. Ortho-para-directing groups are the substituent which direct the other substituent at ortho and para position. Means if one substituent is present, if this substituent is present, it will direct the other functional group to go at ortho and para position or to substitute at ortho and para position. In case of meta-directing group, these meta-directing group, they will make the other functional group to substitute at meta position. So first let's see the examples which are ortho-para-directing and which are meta-directing. So here you can see the example of ortho and para-directing group. In ortho and para-directing group, if these functional groups are present on the aromatic ring at this position, if these functional groups are present, they will direct the other substituent at either ortho position or at para position. So that is why they are called as ortho and para-directing. Means if these functional groups, they are present on the aromatic ring like benzene, then the other functional group which will react with benzene ring, either they will substitute at ortho position or at para position. Oxygen is there, NH2 group is there, NHR is there, NR2 tertiary amine, hydroxy group, OR methoxy group, NHCOR and alkyl group and any aryl group. So these are the groups which are ortho and para-directing group. If they are present on the benzene ring, they will make other functional group to substitute at either ortho position or at para position. Okay, now meta-directing, if these functional group present on the benzene ring, suppose here, then they will direct the other functional group to substitute at this position, at this meta position. So that is why they are called as meta-directing group. Example is NO2 positive or N2 plus, N plus R, SO3H, aldehyde group, then ketonic group, carboxylic group, COR, CONH2 amide group. So if these groups are present here on the benzene ring, they will direct the other functional group to substitute at meta position, these two positions. That is why they are called as meta-directing group. So these are the example of ortho-directing group, these are the example of meta-directing group. So the ortho-para-directing group, they are known as activating group, and the meta-directing group, they are known as deactivating group. This is the exceptional case. The halides or the halogen derivatives, they behave differently. They are deactivating group, but they are ortho-para-directing. Means in the presence of halide, then the ortho and para-directing product will obtain, although halides are deactivating group. So halogen or halides, they are the exceptional case. They are deactivating group but ortho-para-direct. While the remaining functional group which are activating, they are ortho-para-directing, and which are deactivating group, they are meta-directing, except halides. So now let's see in detail about activating group and deactivating group, why they are called as activating group and why the other groups they are called as deactivating group. As we already seen the examples of orthopara or activating groups and meta-directing or deactivating groups. Activating groups are those groups which when present on the benzene ring will activate or make the benzene to react faster, means they increases the reactivity of the benzene. Then benzene will react faster. The rate of reaction will increase. The benzene will react faster. If the presence of any functional group make the benzene ring more reactive, then that is called as activating group. And these activating groups generally they are ortho-para directing group. They will increase the reactivity of benzene as compared to unsubstituted benzene ring. So if the reactivity of substituted benzene ring will increase as compared to unsubstituted benzene ring, then this group is called as activating group. Why? Because it is activating the benzene ring to react faster. So the activating group they makes the benzene nucleus to react faster with the second functional group or with other substituent. And generally these activating group they are ortho-para directing group. The activating groups are generally electron donating group because they will donate the electron to benzene ring and the electrons they will move inside the benzene ring. Due to resonance, the benzene ring will stabilize easily. So these activating group they are electron donating group. These groups they will divert the electron to the ring to make them activate, to make them react faster. So that is why they are called as activating group. So electron donating groups they are activating group. They will give electrons to the ring and due to resonance these ring get stabilized and it will react faster with other substituent. Now let's discuss the deactivating group. Let's take example D is the deactivating group. So if this D is present on the benzene ring, it will make the other substituent to react at meta position. So here it decreases the reactivity of benzene, means the benzene ring will react slowly. So if any group which makes the benzene to react slowly and decreases the reactivity of benzene ring is called as deactivating group. And these deactivating groups they are meta-directing group. Electron withdrawing group are the meta-directing group. They will decrease the electron density on the benzene ring due to which the reactivity will get decreased. If this D is deactivating group, it will take the electrons towards itself and it less stabilize or it decrease the stability of benzene ring. So if electron withdrawing group is present, they will take the electrons toward itself due to inductive effect. So because of this inductive effect, the reactivity of benzene get decreased and it will react slowly. So if it will react slowly, they are called as deactivating group and generally they will direct the other functional group at meta position. So here we can see in ortho-para directing group, the resonance energy play the important role. While in deactivating group, the inductive effect play the important role, means here the inductive effect is dominant. The electrons they will pull from ring to D group. Because of that the reaction will get decreased or the reactivity of benzene will get decreased. So here the reactivity of benzene is increasing in case of activating group. Here the reactivity of benzene is decreasing in case of deactivating group. Here benzene ring will react faster as compared to unsubstituted benzene ring. Here the benzene ring will react slower as compared to unsubstituted benzene ring. Generally the electron donating group they are activating group and electron withdrawing group they are deactivating group. Exceptionals are halide. These halide groups they are deactivating but ortho-para directing. This is the only exceptional case. In case of activating group, the electron density on the ring will get increased So because of that, the benzene ring will become activated. While in case of deactivating group, the electron density on the benzene ring will get decreased. It will destabilize the benzene ring. So the benzene ring will react slowly, or the reactivity of benzene will get decreased. Now let's see that how electron donating group are ortho-para-directing and electron withdrawing group or deactivating group are meta-directing. If the electron donating group present on benzene ring, it is also called as activating group. Let's see the example. So this is the first case where the electron donating group is present. So here you can see the two electrons, lone pair of electrons which is available. So this is the electron donating group and this is the benzene ring. Let's see how this group will affect the substitution of other functional group on benzene ring. So here two lone pair of electron is there and they will form a double bond here, and if these two electrons they will shift at this position, then to maintain the valency this electrons will come here. So this is the first condition. This is S, and if electrons they will move here, because we know that benzene is a resonating structure. So here the movement of electrons will take place in the ring and outside the ring. So here double bond will form and negative charge will appear at this side, because the electrons which are present here in this bond, they are now at ortho position and the remaining two bonds are here. Now next, again the resonance, due to resonance these electrons they will enter inside the ring and this bond will break and electrons will go at para position. So here you can see in this case these lone pair of electrons they enter inside the ring, due to which this bond form, and if this bond has to form, this bond will break and electrons they will go at para position. So here the para position will acquire the negative charge. So again due to resonance this electron will enter and this bond will break. These all are resonating structure which can be interexchanged. So here you can see these electrons when they enter inside the ring, this bond is formed, and this bond, double bond, it will break and electrons they will go at ortho position. Now in next case these electrons again they will enter and this double bond has to break. Again these electrons they will move here and S will get negative charge. So again you can see this is structure 1, this is structure 2, this is structure 3, and this is structure 4, and this is structure 5. So here you can see in all these structures there is a movement of lone pair of electron inside the ring. Ultimately from structure 1 to structure 5th is formed. So here you can see the shifting of electron at ortho position, para position and at ortho position. Here you can see the negative charge they will appear at ortho position, para position and again here on ortho position. So if we will make the resonating structure of these all 5 steps. So as we know that resonance structure is the intermediate of all the structure. So if we have to draw the resonating structure of these 1 to 5th structure, then the resonance structure will be like this. So this is the resonating structure, means when we compile all these structure. So this position, this S will acquire positive charge and here they will acquire the partial negative charge, because you can see ortho negative charge is there because of the electron at this position again and at again this position. So if we will combine all these 5 structure, this is the intermediate structure or resonance structure, intermediate or resonance structure. So this resonance structure is the combination of all these 1, 2, 3, 4 and 5 structure. So here you can see the partial negative charge they are appeared at ortho and para position. So now if any electrophile group will attack, suppose any other substituent will come. Generally the benzene ring or the substituted aromatic ring, they are easily go for substitution reaction. So here if any other substituent or electrophile will come, where it will go? As we know that electrophile have positive charge. The positive charge will attract negative charge. So the possibility that electrophile, it will go to these three places. Either at ortho position at this side, or at this side. So that is why we will get ortho and para substituted products. That is why the electron donating group, they are ortho and para directing group. Because the electrophile, they are positively charged, so they will go at the negative side only, or the negative charge position. So because of that, we know that the electrophile will react either at ortho position or at para position. So the possibility of formation of ortho para product will be more in case of electron donating group. Next, we will discuss about the effect of electron withdrawing group on monosubstituted ring. So this electron withdrawing group, they are also known as meta-directing group or deactivating group. They will decrease the reactivity of monosubstituted benzene ring towards the other substituent or other reagent. So that is why they are called as deactivating group. Now let's see how they will affect the substitution of other functional group on the benzene ring. Take an example. This is benzene ring and this S is the electron withdrawing group. So if electron withdrawing group is present on the benzene ring, let's see what it will affect. This electron withdrawing group, it will try to withdraw the electrons from the benzene ring and it will somehow destabilize the resonating structure of benzene. So let's see if it will take the electron from this bond. Let's see, this bond will break and electrons, they will move to, let's see if the electrons are taken by this S group, because it is electron withdrawing group. It will withdraw the electrons from benzene ring toward itself. So let's see, this is the first case where this bond will break and electrons, they will move to electron withdrawing group. So what would be the effect? This is structure 1. So this S will get negative charge because the electrons are taken by this S. Now as the electrons are taken from this bond, this position positive charge will appear, because the electrons, they are taken by the S. To stabilize this structure, the movement of electron will take place at this position. In structure 2, the movement of this electrons at the deficient site. Now let's see the third structure. What would be the effect? So here, if the movement of electron will take place, then the formation of bond will. So if the bond formation will here, then this electrons, they moved here. Because of that, the double bond will appear. So if double bond will appear, then here the deficiency of electron will occur, because the electrons, they will move here. So at this carbon, the deficiency of electron will be there. Now to maintain the resonance in third structure, let's see, this bond will break and electrons, they will move here at this position to maintain the deficiency. As benzene is a resonating structure, the electrons, they will move at different positions. So in fourth structure, because the electrons, they will move from here to this deficient side, again the deficiency will appear at this position. We will see the fifth structure. Here, if the deficiency of electron will be there, the electrons, they will pull inside the ring which is present on the S, and this is our fifth structure. So first, second, third, fourth and fifth, these all are resonating structure when there is a deficiency of electron occur in the benzene ring. So if now we have to compile all these structure to make a resonance structure in case of electron withdrawing group. So let's see the resonating structure or the compilation of 1, 2, 3, 4, 5, all these structure when we compile. If we will compile all these structure, so we can see in second structure positive charge is appeared, in third structure here positive charge is there, and at fourth structure here positive charge is appeared. So all these will carry the partial positive charge at this ortho position and this para position. So here partial positive charges are there, partial positive charge here and partial positive charge here. So this is the resonating or intermediate structure. So means if we will combine all these 1, 2, 3, 4 and 5th structure, this intermediate structure will form. This is the resonance structure of benzene. Resonance structure. So now the question arises, if any electrophile group will attack or it has to substitute, where it will go? At ortho position and at para position already the positive charge is there, and this electrophile will have positive charge. So only meta positions are there where the possibility of electrophile to react. So that is why the deactivating group, they are meta directing group, because only meta position is left where positive charge is not there. The electrophile is electron deficient, and ortho and para position they also have electron deficiency. So the only possibility of electrophile to go is meta position. So we will get meta substituted product if electron withdrawing group is there, and that is why they are known as deactivating group, and they decreases the reactivity of benzene ring. So we can say that deactivating group are meta directing group. It means electron withdrawing group are deactivating group and they are meta directing group. So now you can understand that why some groups they behave as ortho para directing and some group they are meta directing. Now we are going to discuss the effect of substituents with more examples. Let's take an example of activating group, like if OH group is present on benzene ring, how it will affect the reaction of benzene with other substituent. So let's draw the structure of benzene ring with phenol group. So this is the oxygen with lone pair of electrons. So this is benzene ring with phenolic group. This is benzene ring with OH group. So oxygen have lone pair of electron. So this is the first structure. I am discussing the case where the OH group is present on the benzene ring and OH group is activating group. So let's see how it is ortho para directing group or it is a meta directing group. Okay, so OH is present because this lone pair of electron is there and it is rich in electron. So we can say that OH group is electron donating group. It will divert the electrons towards the ring. So in first structure you can see the electrons, they will try to move here. So to maintain the resonance in the ring, this bond will break and electrons they will move at the ortho position. So this is the first structure. Now let's see what is the effect of these shifting on second structure. As the electrons are moved at this position, here the partial positive charge will appear, and because the electrons they will move at this position, the partial negative charge will appear. So this is the second structure. Due to resonance, this shifting of electron takes place and second structure will be like this. Now again due to resonance, the shifting of electron will occur and these electrons they will enter inside the ring, and to maintain the electron density, these electrons they will move at para position. So in third structure, because the electrons they will enter the inside the ring, the double bond is formed, and as this bond is break, the electrons they will go to para position and it will acquire negative charge. So this is the structure third. Again due to resonance, the shuffling of electron will takes place. So these electrons they will move inside the ring and this bond will break and electrons will go at ortho position. Let's see the fourth structure. These all structures are forming due to resonance. So because the electrons they will move here, negative charge will appear and positive charge. This is the fourth structure. Now let's see the fifth structure. As again there is a shuffling of electron from fourth, these electrons they will move inside the ring and again this bond will break and electrons will go to the oxygen. So let's see the fifth structure. So this is fifth structure. So you can see first, second, third, fourth and fifth, total 5 resonating structures are formed in case of phenol. Now if we will make a resonance structure, means the intermediate structure of all these 5 structure. So resonating structure will be like this. So this is the resonance structure when phenol group is present. When phenol group is present. So this resonance structure is the compilation or combination of structure 1, 2, 3 and 4, 5. So here you can see in resonating structure the partial negative charge. Here you can see on second structure the partial negative charge at ortho position. At third structure it is at para position, and at fourth structure it is again at ortho position. So this is the overall combination of all the structures. Now the question arises, if other functional group or other electrophile have to attack. Suppose if the other substituent and electrophile will attack, where it will go? The electrophile is having positive charge, so it will go to the side where negative charges are present. So possibility of electrophile to go at ortho or para position. So that is why phenol is ortho para directing group. So we can say that phenol is ortho and para directing group. This OH group is ortho and para directing group, and it is activating in nature because it is giving the electrons to the benzene ring, and it will make the benzene ring to react faster with this electrophile. So basically it is activating the benzene ring. So here we can say the phenol is ortho para directing group. You can see the resonance structure, and we found that in resonating structure the ortho position and the para position, these two are ortho position and this is para position, the negative charge will appear. So because of presence of the partial negative charge, the electrophile, they will attach or they will attack or they will substitute at either ortho position or at para position. So you will get the combination of ortho and para product if phenol group is present. So we can say that phenol or the OH group is ortho para directing group. If OH group is present on the benzene ring, the other substituent will be ortho and para product. The other substituent will go at ortho and para position, so we will get ortho and para product. So this is the case when OH group is present on the benzene ring. Now let's see effect of alkyl group. If alkyl group is present on the benzene ring, let's take another example. If CH3 group, methyl group is present, we can write this example for this alkyl group also, the presence of alkyl group, how it will affect the reaction of benzene. Here I am taking the example of methyl group, or we can write simply R. R can be any alkyl group. So let's discuss the example if alkyl group is present on benzene ring. So let's discuss if the CH3 group is present on the benzene ring. So here the carbon or the methyl group does not have any lone pair of electron like the phenol. Okay, but because of the hyperconjugation effect, they will act as a ortho para directing group. So let's see how they will affect the reaction of benzene. So this is the case of methyl benzene. Here this bond will break and electrons, they will go on this carbon. So that is called the hyperconjugation, movement of sigma bond to form a pi bond, means breaking of single bond, and that electrons are utilized to form the double bond, that is called the hyperconjugative effect. These effects are given in methyl compound. So this is our structure 1, where one of the hydrogen and the carbon bond will break and electrons, they are utilized to form a bond, double bond here on this carbon. So ultimately when this bond will, the electrons will shift here, then this bond will break and the electrons, they will move at ortho position. So this is our structure 1. In first case, the bond between carbon and hydrogen will break and electrons are utilized by this carbon. So here remember one thing, this methyl group does not have lone pair of electron, but it will utilize the electrons which are present between the carbon and hydrogen. Now let's see the second structure. This is hydrogen and H plus will remain in the reaction, but it will, here double bond will appear and here negative charge will appear. So this is our structure 2, where you can see this bond is broken and the electrons are utilized to form a double bond. So here this carbon will acquire positive charge, and this position, because due to the shifting of this bond here, the electrons, they will move here. So at ortho position the negative charge will appear. So this is the case of second structure. Now let's see third structure. Here again these electrons, they will move inside the ring because of the resonance, and this bond electrons will shift here. So this is the third structure where the shifting of electrons inside the ring will make double bond, and this bond will break and electrons, they will move here, and this para position will get negative charge. So this is the structure 3rd. Again due to resonance, these electrons, they will move inside the ring and this bond will break and the electrons, they will move at 4th position. So let's see the 4th structure. So this is our 4th structure, where you can see in 3rd structure the electrons, they will move here. So this at 4th position it will acquire negative charge. Again due to resonance, these electrons, they will enter inside the ring and this double bond will break and the electrons are utilized to form a bond, and the electrons are utilized to form a bond with this hydrogen. So in structure 4, the electrons, they will move inside the ring due to resonance and this double bond will break, and again this will be taken by the carbon and hydrogen to form a bond. So let's see the 5th structure. So this is the 5th structure, where you can see again the bond between carbon and hydrogen appear. So now let's draw the resonating structure or the combination of all these 1, 2, 3, 4, 5 structure. If we will combine this. So this is the resonance structure, means the combination of structure 1, 2, 3, 4 and 5. If we will combine all this structure, this resonance structure will form where this carbon will acquire partial positive charge, because here you can see structure 2, 3, 4, it will have positive charge, here double bond partial, and the negative charges, they are present at ortho and para position. So this is the ortho position, this is the para position, where the partial negative charges, they appear. So if any other electrophile have to substitute or to react with this structure, where it will go? It has positive charge, and at ortho and para position the negative charge is there. So obviously these electrophile will attach at either ortho position or at para position. So again we can say the alkyl group or the methyl group, they are ortho and para directing group, and they are also activating group, because although they don't have lone pair of electron, but they are giving the electrons which are present between carbon and hydrogen bond to the aromatic ring. So because of that they are activating. Methyl group or alkyl group, they are activating group, and they are ortho and para directing group. So as you can see, the negative charges appear at ortho and para position. So because of that, the electrophile it will attach at ortho and para site only. So they are called as alkyl group, they are called as ortho para directing group and activating group. Now let's see the exceptional case of halide, that why halogens they are deactivating but still ortho para directing. So here I am discussing if halogen or halide group is there. If halide group is present on benzene ring. See, if halide group is present on benzene ring, how it will affect the reaction. As we know that halide groups are deactivating group, but still they are ortho para directing. Why? If halide group is present, it is electron withdrawing group. So here in benzene two forces will act. One is inductive effect and second is the resonance effect due to a benzene ring. Resonance effect. So these two effects are present when halide react with the benzene ring, but the inductive effect will be dominant over the resonance effect. So the inductive effect is more as compared to resonance effect in benzene ring. So let's see how this halide group they are deactivating but still ortho para directing. The main reason for this is the halide groups they have lone pair of electrons in p shell, means they have unshared p electrons present. Because of that unshared electrons or lone pair of electrons present in the p orbital, they are ortho para directing. Although these halide groups they are inductive effect and they will deactivate the benzene ring because of the electron withdrawing tendency, deactivate benzene ring, but they have lone pair of electron in p orbital. Because of that lone pair of electron, they will act as ortho para directing group. Because of these lone pair of electrons which are present in the p orbital of halogens or halide groups. So let's see how they will act. Let's discuss what will happen if halogen group is present on the benzene ring. Because the halogen they will have a one lone pair of electron in p orbital. Let's see. Let's draw their resonance structure. Let's take an example of chlorine because they have lone pair of electrons. So this is our structure 1, in which again the resonating effect and the inductive effect will be there. Although this chlorine is electron withdrawing, so it has a tendency to move electrons towards itself. But due to this lone pair of electron, the things will change. So here you can see the electrons they are taken. So this is the first case where lone pair of electron is there. So this will go in this resonating structure and this bond will break. So this is the structure 1. Let's draw the structure 2. So this is the structure 2 where you can see the lone pair of electrons from p orbital. They will move here and this chlorine will acquire partial positive charge and this bond it will break and go at ortho position. So at ortho position negative charge will appear. So this is the second structure. Now again due to resonance these electrons they will move inside the ring and this bond will go at, this electron will go at para position. So let's see the third resonating structure or third structure. So this is the structure 3rd where you can see chlorine will have positive charge and the bond formation will take place at this position and this bond will break and they go at 3rd position. So this is the 3rd structure. Now again due to resonance these electrons they will move inside the ring and this bond will break and it will go at ortho position. So let's see the 4th structure. So this is the fourth structure where you can see the electrons, they will move inside the ring and double bond is formed, and here the electrons, they will present at ortho position. Now again, due to resonance, these electrons, they will move inside the ring. And let's see the fifth structure. So this is the fifth structure where you can see the bond formation will appear here, the double bond will appear and lone pair will go on chlorine. So this is the fifth structure. Now let's draw the resonating structure of all these 1, 2, 3, 4, 5. If we will combine these all 5 structure, let's see what will be the resonance structure. So this is the resonance structure if halogen like chlorine group is present. So here you can see the partial positive charge of chlorine because the structure 2, 3 and 4 you can see positive charges there, and at ortho position and para position the negative charges are there. So when we take the average or when we will compile this structure 1 to 5, we will get this type of resonance structure. So now again the question arises, if electrophile has to react, means if electrophile will attack, where it will go? Electrophile is positive charge, then obviously it will go at ortho and para position. So because of that, halides, they are ortho and para directing group. Although they are deactivating because of the inductive effect, but due to lone pair of electron present in the p orbital, because of that lone pair, they became ortho para directing group. So this is the case if halogen is present on the benzene ring like chlorine is there. So because of that, halides, they are deactivating but ortho para directing. They are the exceptional case. Ortho para directing. Halides, they are deactivating group but ortho para directing group. Now let's discuss another example of electron withdrawing group apart from halides. If any electron withdrawing group is present on the aromatic ring, how the benzene ring will behave. So let's take an example of here NO2 group, nitro group. Nitro group is electron withdrawing group and it is a deactivating or meta-directing group. So let's see that how nitro group will affect the reactivity of benzene. So if NO2 group, nitro group is present on benzene ring, it is an electron withdrawing or meta-directing group. You can see the example in activating and deactivating group. So let's see the example. So this is the structure 1. Structure of nitro group where NO2, one nitrogen will have double bond with one of the oxygen and single bond with other oxygen. So this is the case of NO2. Now let's see in resonance how it will act. As it is an electron withdrawing group, let's see the movement of electrons, how it takes place. Because of the electron withdrawing nature, this nitro group, it will try to withdraw the electron from the benzene ring. So here you can say the shifting of electron in double bond at this position. So this is the structure 1. Let's see the structure 2. So this is the structure 2 where you can see the positive charge will appear on this nitrogen because the double bond with having electrons are taken by the oxygen. So here you can see the structure. This is the first structure where NO2 group is there. Nitrogen have double bond oxygen and single bond with this oxygen. So because of that you can see nitro group have electron withdrawing group, so it will try to withdraw electron from double bond to nitrogen. So here you can see in second structure the bond between nitrogen and oxygen will break and electrons will be taken by the oxygen. So the oxygen will carry the negative charge. So here I will indicate it with red color. So nitrogen will get positive charge and oxygen will get negative charge. As nitrogen and ortho group have electron withdrawing tendency, it will try to withdraw electron from this bond to here. So the movement of electron from here to this position, here double bond will appear. As the electron movement from this position to this carbon or this ortho position became electron deficient. So this is the second case. Now let's see the third structure. Due to resonance, this bond will break and electrons, they will move to the deficient side. This bond will break and the electrons, they will move at the deficient carbon. Okay, so this double bond will break and the electrons, due to resonance, they will move at the deficient side. So now let's see the third structure. So this is the third structure. Due to movement of electron from this position to here, the positive charge will appear at the para position. Here you can see the double bond form. Now again the electron deficiency is at third position. So due to resonance, the movement of electron takes place from this bond. Now let's see the fourth structure. So this is the resonance structure of nitro group. Resonance structure. If NO2 group is there, means this is the, you can say this is the intermediate structure of 1, 2, 3, 4, 5 or the combination of all these structures. So here you can see nitrogen have positive charge, as you can see on structure 2, 3, 4, the positive charge, and oxygen will have negative charge, as you can see in structure 2, 3 and 4. And at ortho position positive charges are there, you can see in structure 2, 3 and 4. So it means when we will combine all this structure, we can see at nitrogen group and at ortho and para position the partial positive charge is there. So because of this, if any electrophile will come to react, at which position it will go. Electrophile have positive charge and ortho position and para position they have positive charge. So only one position is left, that is meta position. So it means nitro group is meta-directing group. As nitro group is electron withdrawing group, you can see the electrons, they are withdrawn from the ring. So NO2 is deactivating group and meta-directing group. So nitro group is deactivating group and meta-directing group. Why? Because it is directing the other substituent at meta position. So here you can see ortho and para position will have positive charge. So only meta position is left where this electrophile can form a bond or it can substitute at meta position. So that is why NO2 group is meta-directing group and it is a electron withdrawing group or deactivating group, which is deactivating the ring. It is withdrawing the electron from the benzene ring. Due to the resonance, it tries to stabilize the structure. So that is why you can see by this resonating structure, NO2 group is known as meta-directing group. Dear students, I hope you like this video and now you will have some idea about activating group and deactivating group and why the activating group are ortho-para-directing and deactivating group are meta-directing. Exceptional is the halide group. If you like my video, then please subscribe my channel and share this video with other students so that it will also help them. Thank you for watching my video.